Welcome to Math 1508 Pre-Calculus at the University of Texas, El Paso. This follows along with Larson's 10th edition of Pre-Calculus textbook, Chapter 1, Functions and Their Graphs, Section 1.6, Library of Parent Functions. A fact. First of all, there are some functions that you need to know the general shape of as they are discussed. This needs to be an instant recall and not something you have to look up every time. So if I talk about a quadratic or a squaring function, if I talk about a reciprocal, I need you to be able to visualize it. We will discuss 8 basic functions here and their general shapes and features. They'll be used in later sections more extensively, but for now, just the basics. First, the constant function. And the constant function is f of x equals c, some constant, some real number c. It's a horizontal line, it has slope 0. It's a special case of the identity function or a linear function. The identity function, f of x equals x, is given to us by this graph, the identity function. And the identity function combined with the constant function will give us all of our linear functions. The third basic function is the absolute value function. F of x equals the absolute value of x is a V-shaped graph. We're going to move this at some point, make it wider, make it narrower, shift it right, left, up, down, do a whole bunch of different things with it. But for now, the basic V-shaped graph. The square root function is the top half of a parabola lying on its side. Whereas the quadratic or squaring function, f of x equals x squared, is a parabola that opens up. We'll move it around, we'll flip it around, do things later. The cubic function, it's kind of a lazy S type of function. I guess it's not really an S shaped, but it's like this left side of a parabola just got reflected down. The reciprocal or rational function, f of x equals 1 over x, looks like this. Notice that x equals 0. We do not have a domain value. X can't be 0, can't divide by 0. So we have what's called an asymptote here, and we'll talk more about that in a little bit. The greatest integer function might be the newest function for you, and it looks like a double absolute value, but it's not. Some people call this the ceiling function. Ceiling function, the greatest integer less than or equal to whatever function we're looking at. So we'll talk more about what this is, but it's a general step function, looks like stair steps. Let's look at some examples of this one on the next screens. So the greatest integer looks like double absolute values, as I suggested, but it doesn't work in the same way. What is the greatest integer function? It has an output that represents the greatest integer less than or equal to the input. Think of left of on a number line. The fact is, the output of a greatest integer function is always an integer. Always an integer. Never a fractional, decimal type of number. Always a positive or negative counting number or 0. Let's look at some examples. If the input in the greatest integer function is an integer, the output is that same integer. The greatest integer of 2, what's the greatest integer less than or equal to 2? Well, that's 2. Similarly, the greatest integer of negative 3 is negative 3. If the input is positive, but not an integer, we essentially truncate, and truncate means ignore the decimal. So what's the largest integer less than or equal to 3.7? Well, 3 is the last integer before I get to 3.7. 4 is the last integer before I get to 4.1. 123 is the last integer after I get to 123.4567889. A pretty clever example if you ask me. However, if the input is negative and not an integer, we use the next smallest integer. If I'm going to negative 2.9, think about a number line. Negative 2.9, which integer is to the left of that, immediately to the left? Negative 3 is. Negative 11.3, the greatest integer, would be negative 12, so we step down 1. Now that we have several types of functions, we can put them together in a bunch of different ways to create newer functions called piecewise defined functions, because they're defined in pieces. Okay, so let's look at some piecewise defined functions. This first one, f of x, is the function x plus 6 if x is less than or equal to 4. The function has an output of 1/2 x minus 4 if x is greater than 4. Don't worry, it's not your eyes. The screen keeps fading out. We'll be okay. Now, the cut value of x equals 4 is the only possibility of an open or a closed dot. Everything else, when x is less than 4, when x is greater than 4, we use a solid line. But a cut value, where the domain changes from one piece to the next at x equals 4, we need to check for the possibility of open or closed dots. Let's see when that happens. This top piece, x plus 6, when x is less than or equal to 4. My domain, x is less than or equal to 4. My output, x plus 6. So I'm going to choose values starting at 4 and getting smaller, 4, 3, 2, 1, 0. Because of this or equal to, I remind myself I have a solid dot here next to the 4. 4 plus 6 is 10. 3 plus 6 is 9. 2 plus 6 is 8. 1 plus 6 is 7, and so on. So a solid dot if we have an or equal to. And I could plot these values. 4, 10, 0, 6, all the values in between. And remember, this starts at 4 and goes to the left, less than. Solid dot because I can equal 4 and all values less than. Now I take a look at the second piece, 1/2 x minus 4 for x values greater than 4. Now, since the x values are greater than 4, I'm going to once again start at 4, but I'm going to put an open circle here to remind myself I can't use 4, but I could use something super close to it, like 4.000000001. We don't have any way of writing that. We don't have any desire to write that. So we use an open circle saying everything really close to 4, but not 4 itself. Now I put 4 in. Half of 4 is 2. 2 minus 4 is negative 2. I have no desire to deal with fractions here, so I'm going to move on to 6. Half of 6 is 3. 3 minus 4 is negative 1. Still don't want to use an odd value because I don't want to deal with fractions. So I choose an 8. Half of 8 is 4. 4 minus 4 is 0. And I can plot these values. When x is 4, for the green equation, the green piece of our piecewise defined function, I know my y value is negative 2. At 6, my y value is negative 1, and at 8, my y value is 0, and I can draw my line from there. The x value of 4, the only time we do not have equality, everything else fits, and so everything else is a solid line. Notice, the graph must still pass the vertical line test as it is the graph of a function, and that's why one of the values of x equals 4 is solid, while the other one has to be open. A second example. A little less detail this time, but still. When x is less than or equal to 2, I use a solid dot. 2 and values less, 1, 0, negative 1. I evaluate, making sure to use my order of operations appropriately. For the green part, the square root of x minus 2 for x values greater than 2. I use an open dot at 2. When x is greater than 2, and I use 2, I would get a result of 0. But remember, that's an open circle. When x is greater than 2, 3. 3 minus 2 is 1. Square root of 1 is 1. 4 and 5 give me outputs that are not necessarily nice numbers. They're irrational. I don't really want to graph them. So I move on to numbers that are going to work for me. 6 minus 2 would give me 4. The square root of 4 is 2. 11 minus 2 is 9. Square root of 9 is 3. I can plot my blue values. Close dot at 2, 0. And I can plot my green values, the open circle at 2, 0. And it goes up in a radical form. Let's look at a word problem using a piecewise defined function. And you find this frequently in shift work. A mechanic is paid $14 per hour for regular time and time and a half for overtime. The weekly wage function is given by the wage based on the number of hours worked is 14h for all hours above 0 but less than or equal to 40. And 21, right, because 14 time and a half would be $21 for every hour over 40 plus 560. And we'll get back to this 560 in a minute, but those are for hours over 40. So we have a split domain at 40. Of course, we're not going to work negative hours, so that's just in there for eliminating the ridiculous. We're going to evaluate this function in 4 different locations and then look at a possible new weekly wage where overtime starts after 45 hours. First, we evaluate W of 30. I put in 30 for my H. It's in the top piece. 14 times 30, I'd make $420 before taxes. For a 40-hour week, 40 hours, H equals 40. 14 times 40 gives me 560. Hey, look at that. That's what this 560 is. This is the wage if you worked 40 hours. And then this piece is the amount of pay over 40 hours, combining to give you your total wage. At 45 hours, we'd have $21 for these for the last 5 hours, plus the 560 we get for working our 40 hours, $665. And if we work 50 hours, that's 10 hours of overtime at $21 an hour, plus the $560 for the 40-hour work week to give us $770. It's a nice little wage for the week. Now, the company increased the regular work week to 45 hours. What's the new weekly wage function? Well, now we're going to split it 45. So that's going to change. Still $14 an hour up until 45 hours. Still time and a half for the hours over 45. But notice we had to change this base. 45 hours, 14 times 45, is $630 for a standard 45-hour week, plus the amount of overtime. That completes this example and this section.